go to details, the bottom right corner one is the current meeting in Rome, where I am now, on the FAO's global expert meeting. Next slide, please. So when we talk about the global food security, we will take Singapore as a case in point, because that actually reflects the situation at the macro, at the micro level in Singapore, but it reflects the macro situation in the world. So first, what we see on the left-hand side is shrinking farmland. In Singapore, at the time of our independence, we had about 25% of land allocated for farming. But with the urbanization and the industrialization, the farmland has reduced over the years. You can see at the bottom left corner, right now we have about 1%. If we look at the global level, is also we see similar trend, that is more and more people are living in the urban area, and industrialization and the urbanization actually also competing with the farmland. Second one is the food waste. Food waste is actually some area that the people who are not paying enough attention in the past, but now with the disruption of global food supply chain, people are paying attention more these days. The third one is, for example, in Singapore, as you see the number, do not look at the 791, all these big numbers, just look at the 2 bowl of food waste at the bottom of the orange area. That is the amount of food waste generated in Singapore per person per day. Is it a lot? Well, it's actually quite substantial. The FAO has estimated that 30 to 50% of the food produced, either from farm or from processing, end up as a waste or loss. So the same survey has concluded that if globally we can reduce food waste to zero, there's no need to worry about increasing farmland or even introducing GM crops. So that is the impact on reducing food waste. The third one is the aging population. This again is very typical of Singapore, but also reflect the global trend that is a very fast aging population globally. So if we look at carefully about these 3 areas facing Singapore food security, you can see that there's basic concept of the benefit of circular economy, because when you connect all 3 together, then you will achieve a much more efficient food system. Why is this so? Because if we can reduce food waste, we will need less farmland. And if we can address a nutrition requirement for the aging population, then we can produce the food according to the need. So it's not day in, day out producing the same kind of crops or food as in the past. So it's really what we call it customized food production and crop production, and along the way reduce food waste. So next slide, please. Okay, so when we talk about food waste, is it a common thing to just uniquely Singapore, or is it common beyond Singapore? So this slide, if we just in view of the time constraint, let's just look at the right-hand side, all the circles. If you look at the right-hand side, you see that it's not uniquely Singapore. This is a Southeast Asia situation, different countries. We should not pay attention to the particular situation in a particular country. The key takeaway here is that food waste is a common problem in Southeast Asia. Whether Singapore is on the right-hand side, the second to the bottom on the right-hand side, you can see that Singapore's food waste problem takes up about 10% of the total waste generated in the economy. It looks better than other countries, but that's not the point here. The point here is that innovation developed to solve this problem will have sort of a benefit to everyone in the region. What happened for Singapore's food situation is that we have been importing food from 170 countries, but that is in the past more like a cash transaction, not much of partnership and technology transfer. So moving forward, what we would like to see is to work together to solve a common problem. And in doing so, we build relationship, we build partnership, and then we can work together better to overcome the problem of food security together in the future. So this is the takeaway here is that innovation that we can develop will have a application beyond Singapore. I think this is very important because otherwise we solve our own problem, has no benefit to other people, not necessarily Southeast Asia, but beyond that also. But I see that Southeast Asia is actually really a anchor point to enhance our regional food security in the context of ASEAN, for example. Next slide, please. So these are some of the innovations and opportunity in food waste reduction. So when we talk about food waste reduction, we actually need to consider two approaches moving in opposite direction to complement each other. First, if we just talk about deal with the food waste, it's like firefighting, never ends. The important aspect of food waste reduction is also to reduce food waste at the source. By doing so, we actually sort of help enhance the food system because we maximize the utilization of available food. So that can be done through various ways. In Singapore, what we have developed is to develop natural food preservative, which work better than the chemical preservative used in the current processed food. And when I say it works better, meaning that it would extend the shelf life of food produced, for example, in supermarket. And consumers tend to look at the expiry date of the food produced. If it's a near expiry date, the tendency is that they will not buy. Then therefore generate a lot of waste from supermarket. So what we have developed is actually extend the shelf life of food produced, therefore leading to less waste generated. But of course, that's only one solution, not everything. That we can also talk about smart packaging technology to extend shelf life of food produced. And another area that we can consider is to develop urban agriculture, urban farming, because that will shorten the supply chain distance, leading to the reduced food loss. Because right now, the farms are very far from the cities, and the transport, logistic, all these along the way, moving from crops, farm side to processing and storage side, would generate food loss, right? So this is one solution. So the second approach is about food waste, which has been generated already. Like for example, there will always be food waste generated from food processing industry, for example, like when we make bean curd, when we make soy milk, there will be soybean residue generated in the term that the Mike is familiar with, is called okara. Of course, okara is a delicacy in Japan, but depending on the culture and the region and the country, some countries treat it as waste to be, but there's still a lot of value in all these processing side stream. And so what I show here, the takeaway here is that we will take two approaches. One, to develop innovation to reduce the generation of food waste at the source. Second, to upcycle. The important concept here is upcycle, not food waste, but waste to be. But we pay a lot of attention on what we are working on. We work with processing side streams, not the food waste from restaurant or household, because consumer would unlikely buy anything, food ingredient made of food waste from the household or restaurant. So we focus on food processing side stream like okara. The advantage of using okara, not just okara, also barley spent grain. The advantage of using okra is that it's homogeneous and scalability is high from lab to industry. And in the process, we actually can create this food circular economy. Next slide, please. Next slide, please. Okay, so this summarizes what I just described to you. First, we use existing technology the consumer are familiar with to enhance efficiency of all these innovations. For example, use fermentation to recover nutrient from the okra, the word you see in the middle of the three images at the bottom. First one is the natural food preservative that we have developed. You can see the antimicrobial assay here. This is showing that it's more potent. This is our natural food preservative. This is a commercial chemical preservative. You can see it's so much more potent in terms of antimicrobial activity. This will lead to the extension of shelf life of food produced. These two are related to food circular economy. So I use example of okra. Through solid state fermentation, we recover nutrient from this okra, but fermentation will not dissolve everything in the okra. A lot of solid residue remain behind. So what I developed is to develop this. We have developed this extraction technology to take the fiber out of this okra after fermentation and then biodegradable packaging material. In the process, you can see that soybean come to the processing factory, generate bean curd and soy meal, and leave behind a lot of okra. So what we do is we apply fermentation, take nutrient out, and then convert the remaining residue into something useful. So in the process, all the waste it has been converted into useful material, then create this zero waste food processing and also the food circular economy. So what we do here is using existing technology, right, to enhance efficiency, and also very simple, because we always think of long-term application potential to move beyond the laboratories. So the scalability is high when it's simple. Our innovation usually is 1 or 2 steps. And the platform technology, we emphasize on developing platform technology. For example, fermentation technology can be applied to okra, can be applied to barley spent green that we use to make Milo, that people are familiar with. And zero waste food processing is the end point. Yeah. Okay. Next slide, please. So you may ask, what do you do with the nutrient recovered from the side stream? So I use the example of barley spent green here. So in this case, it's not making Milo, but the process is the same. No offense, this is the beer making process using barley green, right? So in the past, this barley spent green is disposed of as a waste. But through our innovation, as I mentioned, the platform technology, when we apply to barley spent green, and the nutrient recovery can be used to grow yeast. Yeast, as you know, is necessary to make beer, right? The idea here is not to encourage making beer, but is to show the usefulness of this nutrient recovery. The important part here is not simply to replace the commercial culture media, but the important message here is that it will cut the operating cost by 90%. So there's a value add. It is actually what we call upcycle, because it contributes to the sort of economy. You may ask the replacement. So in addition to this yeast culture medium replacement, we have demonstrated that it can also benefit to the alternative food industry. For example, microalgae culture medium can also be replaced using our nutrient recovered from either okra or barley spent green. And more importantly, in the space of cultivated meat industry, the growing of meat in the laboratory without slaughtering animals, That is another growing trend globally. We have demonstrated that the nutrient recovered from this either okra or barley spent green can replace animal-derived serum, which has been used as a critical factor to help the cell proliferate in the bioreactor. So you can see that this value add is not just simply to traditional food industry like making Milo, making beer, but also benefit the future alternative food development by cutting the cost and replace animal-based ingredient in the processed food. So you may ask, what else can you do? So if I share this with you, you may say it looks good, but we don't know what's inside the nutrient recover, right? You're absolutely right. So what we have done is we move one level up by separating the protein and peptide fraction from the recovered nutrient. And then we have demonstrated, as you see here, that this separate fraction can function as an emulsifier or binding agent. What is emulsifier and binding agent? Typically, when you go to you eat French fries with mayonnaise, the mayonnaise, the oil and water are not separated. They are in the homogeneous same phase with the help of the binding agent. Likewise, chili sauce, oyster sauce is the same thing. The binding agent for the mayonnaise is actually animal-based from egg yolk. So what we have demonstrated is that the egg yolk part, the binding agent, can be replaced by the peptide and protein fraction separated from the nutrient recovered from barley spent green. So this is demonstrated in the process where created this plant-based mayonnaise without egg yolk. And the reporter from Swiss Time has tasted it and give us 95 out of 100 marks. Is really a sort of a proof of concept and proof of value. It would depend on our further partnership with the industry. Next slide, please. I think this is my last slide. So to summarize my talk today, we have demonstrated that current food system can be enhanced through simple innovation. There are many areas for enhancement, but today I focus on food waste valorization. And the case in point here is on the processing side streams, not the household food waste. We have demonstrated through fermentation, we can actually recover nutrient that can be applied to the current food industry and also help to develop future alternative food industry. And to reduce food waste at the source, we actually have developed plant-based food preservatives, which will help extend the shelf life of food produced in the supermarket, for example. And the remaining residue, we also can convert them into biodegradable packaging material. So in the process, we have created this food circular economy. But this is just one of the many areas we are working on. So we really welcome further discussion and the interaction to build the partnership with the Bandung Institute. My email address is here, and thank you so much for your attention. I can stay back for 2 minutes if you have time for a quick question and answer. Thank you.
Thank you so much for Professor William for your very impressive presentation. I heard from the committee that Professor William will no longer here. I'm sorry. Only this moment, yeah. Panitia, would you, Professor William will leave for a while or?
No, I will not have time to come back. So if you have any questions, I will welcome them. But if that introduce disruptions, I will leave now. Yeah, no problem. I'm open. Yeah, I can stay back for a while if there are any questions from the audience or from the panel.
Okay, please. I think because the Professor Liam will leave from the States, I think we invite some questions Is there any question from for Professor William? Because yeah, Professor William talk about the technology innovation for food circular economy and efficient food system. Is there any from floor? Okay, Dr. Dianika, yeah, I think she will have some questions. Ada mic, yeah.
Okay, good afternoon. First of all, I would like to greet you, Professor William. I
Good
know you.
afternoon.
Nice to meet you. My Purnomo Gunawan is my classmate, so that's how we finally we meet each other. So thank you very much for coming in our seminar. So I have
Thank you.
questions. So it's very interesting that about that we face increasing food demand, and while the farmland is shrinking, we can minimize the effect by reducing the food waste. And you mentioned the example of okara, and I wonder what is how can we determine which food waste? Well, you mentioned that household is not an option. Restaurant waste is also not an option, but we have also a lot of agricultural residues. So what is the criteria for us to decide which food waste we can upcycle, for example, or process further, that we have the sustainable process also? Thank you very much.
Thank you. Thank you. This is a very important question. I would say that doing some homework is very important to start any innovation. So in this case, I would suggest that we do some composition analysis on the agriculture byproduct. For example, if you talk about rice browns or coffee brown, all these are a lot of high value in these side streams. If you talk about rice straw, I would say is simply fiber rich, so probably not much of other nutrients. So fiber rich, we can think of making them into packaging materials. Of course, packaging materials is sort of people consider it as low VAT. You are competing with petrochemical derived clean film or other packaging materials. So the question here is actually to make this agriculture or other type of processing stream into useful material, not necessarily competing with low-end, not low-cost petrochemical packaging materials. In terms of household food waste and the restaurant food waste, I think there's a lot of education to be done before we can apply any innovation. For it, one example is first is to reduce overconsumption, and the second one is educate consumers and the F&B sector to start the sorting exercise, the sorting practice, meaning that you can separate carb-rich rice, for example, from lipid-rich waste cooking oil, and also maybe protein-rich type of meat byproduct. And for example, regarding the waste cooking oil, we have a separate technology to convert this, use this waste cooking oil as carbon source to grow microbe, which can produce naturally, I emphasize on natural process, naturally carotenoid, which is a very high value food ingredient, food color that we are all familiar with. Carotenoid being the color that we see in the carrot. Yeah. So this is in some my humble view on how we start the innovations on reducing food waste. So composition analysis first, and then we can design other approaches. Yeah.
Okay, thank you, Professor William. How about the answer, Dr. Andronikas? It's okay for you. Thank you, Professor William. Is there any other questions? We invite one more questions from the floor. Maybe who I will point out. Pak Dr. Pramujo, is there any questions? Please? No. Okay, I think maybe I have some questions, regarding your presentations, Professor William. I read in your presentation that Singapore generated 600,000 about food waste. How did the Singapore authority process this food waste? Doing some conversion to biogas or upcycling, or maybe you can give some example, of your country policy about the food waste, because in our country, in Indonesia, is still a very big problem, the food waste, because they're very low shelf life, and then also can make our environment become more bad and badly. Would you give some answer about this one? Thank you so much, Professor Lim.
Thank you. Thank you for the very important question. In Singapore, the current practice is to send for incinerator, and some small practice that emerging is to use biodigester to convert this food waste into either compost or fertilizer. But Singapore is a small country. It should not be seen as generating compost and fertilizer just because we have a lot of food waste. I think the key is to reduce generation of food waste. In terms of incineration, food waste tend to be high in water content. So it had two problems here. When we burn the food waste, we're essentially burning water and then increase the carbon footprint. So it's not a best practice. In terms of using food waste to generate biogas, is actually one of the practice also in Singapore. But in my view, it's not the best way to sort of generate energy from food waste, because ultimately it's about the you will still have a lot of residue remain behind. So how do you deal with that? The sludge, how do you deal with that? That's another challenge. We're like kicking the can down the road. Eventually, we still have to face the waste problem. And so, in my view, the food waste issue is complex, but we need to categorize them. First, we deal with processing food waste, waste to be, not food waste. So that is already one step towards the right direction. Second, these nutrient recovery innovations can be applied to food waste from household and F&B if they are properly sorted. So because depending on the composition, as I mentioned earlier, we can actually design appropriate approach to upcycle this waste to be into a new ingredient. One example is again, I don't mean to promote anything in particular, but one of the innovations developed in England and later replicated in Singapore is to use leftover bread to make beer, for example. But I try to be sensitive here. So I would rather use wheat cooking oil that we have developed innovation to convert wheat cooking oil into high-value carotenoid. So what I'm trying to say here is that if we can work together, first by sorting out these food waste into different categories depending on the composition, and afterwards we will be able to develop design innovation to convert these categorized waste to material. Thank you.
Okay, thank you, Professor Liam, for your answers. I think give our people here the insight to how to process the food waste. Thank you so much, Professor Liam, and we will present you the certificate. Yeah, thank you so much for your presentation today. Yeah, I
Thank
think
you so much. Thank you.
the certificate
Thank you for having
will.
here. Looking
Yeah.
forward for future partnership. Bye.
Yeah, please wait for a moment, Professor William. This is the certificate for you from our committee, the certificate. Yeah.
Thank you.
And I
Thank
will
you so much.
They will take the picture, and the origin one will send to you as soon as possible.
Thank you. Thank you so much.
Thank you so much,
Have a
Professor
pleasant,
William.
enjoy fruitful discussion after I leave. Thank you. Bye bye.
Yeah, thank you.
Bye.
Thank you so much. Okay, ladies and gentlemen, all participants, yeah, we give applause to Professor William. And then I think we will continue our presentation, yeah, to Mr. Mike Suzuki, I think. Please, Mr. Mike Suzuki, to appear.
Hello, can you hear
to
me?
the camera, yeah. And I heard that you will directly share the screen, yeah?
Yes. Is it okay to sharing from my side?
Okay, yeah, please.
Okay,
please give
I will do that.
the authorization. Okay,
Yes,
please. Yeah, this
Just
is the time is yours, Mr. Mike Suzuki.
Okay, thank you. Can you see my first
Yes,
screen? Okay.
I can see and
Okay.
hear. Yes.
Thank you very much for my introduction, and thank you so much for giving this great opportunity for me. And now I am making a presentation from Japan. I eat a lot of okara, and in case of Japan, if we go to like a tofu shop, yeah, you can also buy okara, and then we normally stir fry okara with vegetable. That is the one of my favorite food. My name is Mike Suzuki, working in Asbill Corporation. And Asbill starts from Japan as measurement and control, and also providing energy saving solution for industries. And the food and beverage industry is one of our important segments for Asbill Corporation. And I am also an active member of Japan Electronics and Information Technology Industry Association. The name is JEITA, JEITA. And one of the JEITA activity is dissemination of energy saving solution to ASEAN industries. And at the beginning, let me show you the Renkei control video. Renkei, R-E-N-K-E-I. Renkei is one of Japanese word, meaning is collaboration. And the Renkei control is one of the solution which efficiently reduce greenhouse gas emission from your utility plant. So at the beginning, let me show you the video. Just a moment, please.
Renkei, the quick win solution that can save the world from global warming. Why not get started right away? What does Renkei mean? Renkei is Japanese for people coming together, collaborating to achieve their objectives. Renkei control optimizes the operation of equipment with high energy demand in buildings, factories, and cities, coordinating between them. This accelerates CO2 reductions in order to realize carbon neutrality. Why not Renkei with us, right now, for the future of our planet? Contact JETA if you are interested in creating a brighter future together.
So this is my today's agenda. What is Renkei control and step of the Renkei control project, and example of Renkei control project, and the application and the scalability of the Renkei control, and the potential for the CO2 emission reduction by Renkei control. So I will start from what is Renkei control. So the meaning of Japanese word Renkei. The meaning of the Renkei is collaboration by multiple people to achieve some target. In our case, we use Renkei to collaborate multiple equipment to work together for optimum use of energy through control. For example, if you have multiple boilers and turbines, you will have many combination of operation to provide electric which satisfy your factory side demand. And which boiler should be used, what is the best load for the boiler, which turbine should be used, what load is good for the turbine. Even if the satisfying the customer side factory demand for the electric and for the steam, there are so many ways to operate boiler and turbine. So depending on the operation, total efficiency are very different. So Renkei control will realize best total efficiency by optimization control. So as a result, we can reduce the greenhouse gas the emission. So Renkei control can optimize operation of the industrial sector, such as utility plant and manufacturing process, and also building sector for the air conditioning system. So then improving their energy efficiency and reducing CO2 emission. So Renkei control can help customer to solve energy management issue, saving energy and reducing CO2. And the Renkei control is a software optimization technology for customer who would like to achieve energy performance improvement without having major renewal or adding expensive equipment into your existing facilities. So this is a totally software approach. There are several types of Renkei control can be defined based on the boundary for the optimization. For example, supply side, which means utility side, supply side Renkei to optimize the operation in the utility plant. And the demand side, which is like a manufacturing process side, demand side Renkei to optimize operation of the manufacturing process. And also supply demand Renkei to collaborating between utility plant and the manufacturing plant to achieve overall optimization. So implementation of the Renkei control technology comparing to the hardware approaches, such as like a replacement with high efficiency equipment, the Renkei is more like a cost effective and shorter construction period. So maybe we can say that this Renkei control approach is quick win approach to contribute to like Indonesian and also ASEAN greenhouse gas reduction target. So let me use the utility plant with cogeneration system and the chillers as an example to understand more about the role of Renkei control. So this utility plant here purchasing the primary energy, which are electricity and natural gas. And this plant needs to generate 3 utilities, which are power, chilled water, and steam. To satisfying power demand from the manufacturing process, operator needs to decide whether to buy more electricity from outside the grid or buy natural gas to produce electricity by their own gas turbine. And for the chilled water, operator also needs to decide between if they have like a turbo chiller and the absorption chiller and the different type of the chiller and the multiple chiller. And also if they have like the thermal storage tank, they need to considering about those operations. And the steam can be produced from the waste heat boiler of the gas turbine or like a gas firing boiler. So there are so many things to consider when operating these equipment together, like such as the cost of primary energy or total efficiency and CO2 emission. So these operations are based on the operator's own skills and know-how to decide the best set point of operation. So operators control the utility plant by using the existing control system. Depending on the operator, there are difference for the operation and difficult to know the best operation. So there are big chance for the like energy saving or like a GHG reduction. The Renke control is optimization software. We just need to install PC server to host the Renke control software on top of the existing control system. Renke control will help operator to do all the calculation needed and also considering the required constraint and the information to achieve optimal operation of the utility system for achieving energy saving. We can define the objective function. It could be minimize of the GHG emission or minimizing of the energy cost. So Renke control can directly give the optimized set point for each equipment through the existing control system, improving the overall energy efficiency of the entire utility plant to fulfill the demand while minimizing the CO2 emission and the energy consumption. Also, Renke control will reduce the burden of the utility operator. So these are the major applicable facility for Renke control. Renke can apply many kinds of utility facility for industries and also can apply like a district cooling plant and a smart city for energy optimization. And also from now on, we will have more advancement in cleaner technology such as renewable energy or like a hydrogen or like a high efficiency equipment or like the big energy storage. The Renke control always can be the core for integration of this technology to achieve maximization of the total energy efficiency. So the next one is a step of the Renke control project. So this is the chart for the Renke control project. So from step number 1 to step number 3 is the project initiation, review and the feasibility study, and to check the applicability of the Renke control into the target boundary and evaluate the energy saving amount. So then step 4 and the step 5 is a Renke control software and the system design and the implementation stage. This will be taking around like 4 to 6 months, from 4 to 6 months, which is much shorter than hardware renewal project. Control is a very quick win, low-hanging fruit to improve like energy efficiency. So from now, let me explain about some example of the Renke control project. So this is an example for the compressed air. So compressed air is used for the range of the food and beverage application. For example, including like product transportation and storage or cooling, spraying, and the cleaning and the packaging, like etc. Quality of the air for the food industry is the most important. But after achieving quality and the safety of the compressed air, we need to considering about the energy saving from the air compressor plant itself. So this compressed air facility, in this example, there is a left-hand side, like a 4 air compressor, and supplies compressed air to the right-hand side, two manufacturing plant A and B through receiver tank and the header piping. So compressor with different capacity and type have been installed through plant expansion and renovation work. So it consists of one large capacity of, let's say, like a turbo compressor, two small capacity, different type of screw compressor, and one screw compressor has like an inverter for the capacity adjustment function. So as for existing control, before the Renke control introduction, each compressor performs individual discharge pressure control by the basic PID control loop. So here we introduce like two examples of Renke control implementation. The first one is to optimize the operation of the compressor in supply utility plant. The second is supply and demand side Renke control, in which not only supply equipment optimization but also demand side optimization. So at the beginning, let me explain about supply side Renke control. So this control keeps receiver tank pressure as constant by changing the combination of the compressor and changing the load of the compressor with like an inverter. So by Renke control, one small capacity screw compressor and one large capacity turbo compressor are repeatedly operate and stopped according to the demand level. These compressors then run at full load as much as possible to avoid inefficient partial load. So only the inverter type, like the compressor, adjusting the load, and the other compressor is the always running, like 100% load, nominal load. So because that is the most efficient. And to checking the demand level, always stop the unnecessary compressor. That is will be realized the very high efficient the unit control for the air compressor. So, and then second example is like supply and demand side, like a total optimization Renke control. And in the supply side, as I already explained, Renke control keep receiver tank pressure as constant by changing the combination of the compressor and changing the load of the compressor of the inverter type. So in this example, there are two factories, A and B. And even if there is a difference in the pressure required by each factory, excessive compressed air are sent because they are connected to by common header. So in order to reduce this waste, a pressure control valve is installed at the entrance from the header pipe to each factory, and the PID control is performed so that terminal pressure at each factory is an appropriate value. So as a result, when the demand of the factory drops, the degree of opening of the pressure control valve is reduced. So this is opportunity for the next level of the energy saving. So in this timing, it is okay to reduce receiver tank air pressure until this pressure control valve fully open. So Renke control is checking this valve position and setting the optimum pressure set point for the receiver tank. So this Renke control will realize a big energy saving. So before the introduction of the Renke control, there was a pressure fluctuation indicated by the green arrow in a trend, and by unit control and the inverter load control and stabilizing header pressure and improve total efficiency of the compressors. Then as a next step, reducing the pressure for the receiver tank by checking the valve position of the demand side. So by reducing the operating pressure by 0.1 megapascal, we can expect an energy saving effect approximately around 20%. So, and also including a reduction in compressor power consumption and also reduction in the leakage. So this is like an example of the Renke control for the air compressor plant, which are using many example in the food industry. So Renke control is like a multi-purpose optimization software. It can be used many type of like a utility plant. Also, it is possible to be scale up. And also with the advancement in the cleaner technology, in the future, we will have more renewable energy and a new fuel, like such as ammonia or hydrogen, and also like a much better like individual equipment or like a better energy storage and the cost cheaper like energy storage. But Renke control will always be the center for this integration, for this technology, because for this integration, it is necessary to have Renke and optimization algorithm. So for better harmonization together to achieve maximization of the total energy efficiency through optimization technology, the Renke will be like a core. This is like our study with ITV and also Thailand Chulalongkorn University and also Vietnam like Hanoi University. We are estimating around like a 5 million ton CO2 per year saving by Renke control from the ASEAN like the industries. And as you see, the Indonesia has like the biggest potential for the GHG emission reduction by Renke control. And this is my last slide for showing like my company Asbil job reference for Renke control in Indonesia. So this article is about optimization control for boiler plant for PT Pertamina in Cilacap. So their facility has 9 high pressure boiler for power generation and also for the refinery process. This steam will be used for the power generation and for the refinery process. So we have implemented the Renke control for this plant and realize optimal number of boilers to run and also optimum boiler load allocation we did. As a result, we could achieve 35,000 tons CO2 reduction per year. And this at that time, this was like a $3 million like a cost saving. So this project was registered as Joint Pledged Mechanism project between Indonesian government and Japanese government. So this CO2 reduction was officially registered as like a CO2 credit. So this is the end of my presentation. I hope my presentation is like some value for the participants for the seminar. And JETA and Asbil will make an effort to contribute to carbon neutrality for the Indonesia. And at the end, I would like to express my gratitude to like Ahmad Zainal Abidin, who supported me a lot, a long time, and also he is now focusing on the like a project Masalo, trying to like a waste to make it like a fertilizer. Yeah. So thank you so much for your attention. Thank you very much.
Thank you very much, Mr. Mike Suzuki. Give applause to Mr. Mike. Thank you. Mr. Mike already finished the presentations, and then please stay here, Mr. Mike, and we will continue directly to Professor Yazid to present, to share the screen, I think, the development of rice husk simultaneous processing technology for amorphous biosilica product and sustainable small-scale electric generation. Please, Bapak Yazid, Professor Yazid.
Thank you, Pak Tirgo, as a chairman. I would like to thank to the committee who invite me to as the My topic on my presentation is the work with my colleague, Dr. Elvi Restiwati, and also my former student, Dr. Steven. The topic is the development of rice husk simultaneous processing technology for amorphous biosilica product and sustainable small-scale electric generation. The difference in this work, because we impose several restrictions due to that we want to produce simultaneously amorphous biosilica. So we don't want to have the product for crystalline one. So we impose the combustion temperature to combust rice husk is not more than 700 C. So that we have to find a way how to combust the rice husk to produce energy and also to produce simultaneously the amorphous content around the ash itself consists of more than 90% of silica. So at the same time, we combust rice husk, then we obtain the biosilica. Then the energy should be converted to electric. So we can produce at the same time the electric energy from the combustion, and then we can obtain the product for the amorphous biosilica. Then the second one is also we try to complete this project, this research, in order to implement in the field. And the third one, we impose the restriction. The scale should not be very large scale that can be distributed any field of rice, so then we can you can produce biosilica and also electrical. And in this case, we don't want to involve any fossil fuel. So now there is nothing fossil fuel involved in the production. So we use all the energy from husk, then the production is without any involvement of the fossil fuel. So Indonesia itself has a biomass stock in various sources, so that this can sorry, this is my side. Okay, we have various biomass resources based on the grass-based biomass, palm oil biomass, and also rice-based biomass and corn-based biomass and others, so that we can employ this biomass source, become the source for the economy, for increasing its economic value. So here around, yeah. Yeah. Sorry. Yeah. It's around 200 billion ton, yeah, altogether, yeah. Then we try to, sorry. Yeah, the topic for our research employ various topic. From the first one, we employ mass and energy balance, chemical thermodynamic, and heat and mass transfer. Then we employ also the science for gel science, engineering drawing, and combustion experiment, and multi-solo simulation. So in this thing we can draw any knowledge and engineering practical to construct the process to produce biosilica and also energy all together at the same time. Okay, this is the background. We employ about the rice husk. Yeah. Since we have Indonesia produce alone around more than 7 million ton paddies, and within paddies we have around 20% ash, then around 20 million ton per year ash, and with this resources we can increase the economic value, and also the energy itself is extracted at the same time when we produce the biosilica. In this case, we specifically produce very small scale and electrical generation. We choose the organic Rankine cycle that is available right now in the market. Just connects our energy resources like hot thermal oil, and then we can generate the electric for the use in the plant. So the rice husk itself, this rice husk, the low caloric value around 13 to 14 megajoule per kilogram, and the ash around 15 to 20%, and in the ash itself around 90% the content is silica. So when look at the global and Indonesian cases, global rice production reaching around 800 million ton per year. It is found widely in Asia, 91% of that from Asia. And Indonesian case here for the paddy, around 70 to 90 million ton rice production. In rice husk itself, we have the capability reach around 20 million ton per year. Yeah. So about the application of amorphous silica here, that the purity around 90% that we can produce from rice husk. So the application is various for building, chemical, industrial, material requirement, electronic, thermal processing, absorbent, and also here pharmaceutical, healthcare, food sensor. So that's we can have the source for amorphous silica to be continued to the end product. Yeah. Yeah. Because of it, we impose several constraints on process development, so we have to optimize the condition of the combustion itself. Yeah. Yeah. So the RAHAS iteration that we want to have maximized biosilica production, we have to maximize the energy production. In this case, we produce the electric. Then we do not allow the inside of the furnace temperature is larger than 700. We don't want the crystalline biosilica is to be produced. So how we choose the combustion system? In this case, we choose higher air. Yeah. Then the system have to be found in the right way. So we choose to call it suspension combustion. Yeah. So this is the system that we develop. Yeah, the system we develop, the suspension combustion. We push the rice husk into the furnace, the rice husk itself is suspended within the furnace volume. Then on the top, we extract the energy that is produced from the combustion with the thermal oil, and the thermal oil we connect it to organic Rankine cycles, then we can produce the electricity right away, and then the thermal oil is returned back to be used to extract the energy inside the combustor. Then here the combustion itself occurs inside with the higher ratio of excess air, around 5 times. So the rice husk itself is suspended inside the volume, and then the combustion occur completely inside the combustor, and then we try to extract the ash, and the ash itself, this is cyclone, and we can also extract from the bottom of the furnace. Then we continue to process the ash itself by process, we call it acid leaching, and also we call it aging. Then we refine the biosilica, and then they can produce the silica that is also has been refined. So this Rankine itself is available in the market, from 10 kilowatt, 20 kilowatt, 50 kilowatt, and then 100 kilowatts. So this one is very complex. Yeah. In terms of the knowledge of combustion that we employ here, we call it very low combustion, around 700. So we try to study about the combustion stages, and then we, in this case, we should do very carefully in order not to achieve the temperature above 700. So we try to study deeply about the combustion stages that occur for the rice husk. So this is study the combustion stages. When we look at here, we try to calculate to simulate the combustion of the rice husk by, they call it realistic decomposition. So then we can predict the temperature inside the furnace very precisely. Yeah. Here that we try to construct the knowledge for the realistic decomposition of the rice husk combustion. So in this case, we make sure that the temperature inside the combustor around 700 in order to have the amorphous biosilica. So this is our studies about various composition for the air that is supplied to the furnace in order to find the right temperature inside the furnace. Yeah. We can achieve around 700. Yeah. So with those information we collect from the research, then we can try to simulate. Yeah, we use Aspen Plus for the process to find to study the effect of any parameter. So we can this simulation we extract from the knowledge that we extract from our experiment. Okay. Next, so when we have some knowledge about the combustion, how this knowledge can be used to design the combustor. Very precisely. So we use the knowledge for the turbulent multi-phase flow. Then we try this to solve all the flow equation inside the turbulent flow and also the particle movement, the combustion that involve inside. We use the simulation, CFD simulation on this, so we can manage to design the geometry of the combustor that ensure the combustion temperature inside not more than 700. So this, so we employ and we find how the movement of the rush hours, how the fluid dynamic behavior inside. So with various geometry that we design. So here the combustor is soft because it is imposed, that's not very big, and also modular system. Okay. So we try to build we call it for the cold test experiment with the fiberglass, so we can find how the rice husk, whether we can ensure that the rice husk will be suspended inside the chamber. So in this case, what we design, what we find in the cold flow, it is very good. The simulation and experiments, the results are very close to each other, so we can conclude to move how to design for the combustor that involve for the combustion system for the rice house. Okay, so for that case, we try to find we call it the ignition temperature for the single rice house. So we develop our equipment here. We found when the rice husk start to combust. So we find around 400 C. So that means that we have to make sure when the rice husk is inserted to the furnace that directly combusted, because the temperature around the rice husk itself around 400. So it will the combustion try to ignite. Here we build our suspension combustion equipment furnace. So we based on the simulation, and then we try to study the behavior of the combustion inside the furnace, the suspension furnace. Okay, we found that accurately the suspension furnace behavior achieve the temperature not exceed 700. So that means with the base of this knowledge, we can continue to build later on the furnace. It's not very big furnace, but smaller furnace, very compact design. Therefore, we can use in the field for the distributed plant, not centralized one. Okay, this is our ash characteristic. We find that to make sure the biosilica, the ash itself inside contain most porous biosilica. Okay, then we extract the silica from rice husk ash. So we develop the process itself, the scenario of the process. Okay, we try to optimize the condition operation. Then finally, we produce the biosilica with a very white color. Yeah, we try to test the usage of biosilica here for the water extraction. Yeah. Here's our techno-economic analysis. Yeah. Based on this techno-economic analysis, we can employ this process for a very small capacity. Based on, we calculate 300 hectare for the rice field. Yeah, we develop the detail, the process, yeah, from the rice house to produce amorphous biosilica and also to produce the electricity based on our organic Rankine cycle. Finally, we try to propose the business of this process that we develop. We put it, we base on land requirement 300 hectare. Yeah. Then we can produce 160 kilowatt electric from organic Rankine cycle, and we can produce biosilica per year, 500 ton per year, and also we can combine with solar energy plant section within the land 300 hectares. So the next step here for the process development, we try for the finding or improving the technological reading level to 6 to 9. At this time, yeah, around 6 TRL. So that concludes my sharing with you what we have done in the last 5 years. Hopefully, we can continue in the future. Thank you very much.
Thank you so much, Professor Yazid. Yeah. Okay, I think we already have 2 speakers that have been presented the slides. Yeah, and then I think we have to go to the Q&A session now. Mr. Mike Suzuki, are you still there?
Yes.
Okay, thank you so much. We will wait the question from the floor, and then please, I think to answer the questions. Thank you so much for that. Okay, we will invite 2 questions first, I think, or 3 maybe from my left-hand side, and then from the middle, and then from the our right-hand side. Yeah. Please, I think Mr. Mike Suzuki already presented about the control system. Yeah, control system to enhance the efficiency, to enhance the or to lower the CO2 emissions. Yeah, I think this is a kind of electronics or control system, some kind like SCADA. Yeah, maybe. Mr. Mike Suzuki. Okay.
Yes, that can be like a SCADA system or like a distributed control system or PLC system. But my agenda was the customer already having those kind of like a control system, and then operator is operating the utility plant for the manufacturing process. For example, like an air compressor plant. They are operating through those SCADA. But there is a variation of the operation, and also there is so many ways to provide the same amount of like a utility, like a compressed air, for example. So in this case, we put on one PC server on the top of the like existing control system. Then instead of the operation team, this PC server will download like an optimal set point, which reduce the energy consumption or CO2 emission reduction to realize. So that kind of like a system is like Rankine control. Thank you.
Yeah, thank you so much, Mr. Mike. Yeah, that's some explanation. Yeah, the short explanation about the systems. Maybe is there any other questions? Okay, from the middle or from the right. Okay, maybe please come to the mic. Yeah. Please introduce yourself. Thank you.
Thank you for the opportunity. Firstly, good afternoon, Mr. Mike Suzuki. Let me introduce myself to you. My name is Stksr Putra from Bioenergy and Chemical Energy Engineering of Bandung Institute of Technology. So, I wondered of how Renki can work in Indonesia. If we take a look, the difference between Indonesia and Japan, Indonesia is one of the biggest country with the diversity in the world, but Indonesia also have the problem that Indonesia also face the global emission because of the industrial activity in Indonesia. It means that the problem is very complicated if we compare to the number of Indonesian forests that Indonesia have. So I would like to ask to you, what do you think if we use the implementation of RENK to reduce the emission in Indonesia and maximizing the energy and use of the energy use and minimizing the use of carbon in industrial activity in Indonesia? Do you think it will work effectively in Indonesia? As we know that Indonesia is a very spacious and have the different industrial culture between one region and the other region. Thank you.
Okay, Mr. Mike, please. Thank you so much in advance.
Thank you very much for the question. And actually, I'm not so sure the difference culture between the region. But I think the carbon neutrality is the one of the subject in the world that all country needs to considering to reduce the greenhouse gas and trying to make it like a zero year 2050, and in some country the target year 2060. So the still I guess I think in my understanding that Indonesia is like a population is growing up, so that is totally different from Japan. So it is necessary to concentrate to the mass production. That means increase the capacity. But increase the capacity, of course, if they do not, if the Indonesian industry does not taking care of the CO2 emission reduction, the absolute value for the CO2 emission will be just increased. So so in such a case, we need to considering about energy index. So to reduce the energy index is the important for the Indonesian industries. Even if the increase the production amount, if you reduce energy index, and that is meaning is that you can reduce the CO2 emission, emission. So I think our approach is also we need to considering about a return on investment, because the CO2 emission reduction is the critical subject, but also it requires some kind of investment. So to reproduce all utility to the renewable side, it will cost much. My point was the ranking control. In case of ranking control, we change the operation. So we are keeping to you existing control system, and also existing equipment such as a boiler, turbine, or air compressor or pumping. But by changing the operation by control, we can reduce some amount of the CO2 emission. So Our benchmark is the saving around like a 10% of the like CO2 emission by control. So I think I'm not sure I'm answering your question or not, but I think not only to focusing on the like capacity, increase the capacity. Also, I think your country is considering about like a CO2 emission reduction. So in this case, Ranking control can have the like some kind of like contribution, and I can say like a quick win solution or low hanging fruit. Actually, the changing the operation is you can start from tomorrow. So that's my question. That's my answer for you. Thank you.
Thank you, Mr. Mike, for the very comprehensive answer. Okay, we will invite again, maybe for Professor Yazid. Maybe you are all here curious about the systems, or maybe how to convert the raw silica to pure silica, the very white, white color silica. I think this is very interesting because Professor Yazid combine of the heat that use to doing some carbonization of the rice husk, and then the heat is used for what we call electricity generation. Okay, maybe you can ask about the efficiency or how much the scale, please. Is there any the mic? Oh yeah, Pak Yanus also.
Good afternoon. Thank you for the chance to ask question. Pak Yazid, my name is Nanik Purwanti. I'm from IPB University. We also did a lot of works on biomass utilization there. My questions about the flow chart of the process that you already shared. What is the energy ratio between the energy value that is generated by the combustion heat and the energy that is required to do the combustion? That's the first question. And the second is that you show that the silica content in rice husks is the highest compared to other biomass there. But if, for example, we choose the other biomass with lower silica content, do you think that will affect the energy ratio that is produced during the combustion? And then the last one is, what is the yield of the silica produced from the rice husk compared to the wet rice husks that you use as raw material? Thank you.
Test.
Okay, yeah. For the yield itself, rice husk contain around 20% ash. Then when we extract the biosilica from the ash itself, we obtain the yield around 95% from the ash. So total yield around 0.2 times 0.95. Total yield from the rice husk itself. From the energy production, we don't really input any energy from outside. So we produce the electricity. So there is no input energy from outside. For the furnace, because the rice husk occur the combustion reaction, so it generates the thermal energy. Some of the thermal energy extracts it with the thermal oil. The thermal oil will be heated, and then temperature around 150. then we can input it to the organic Rankine cycle, and then we can produce the electricity. So the energy itself is a surplus based on the electricity that we produce. Yeah. So that's why we don't employ any fossil fuel to the process. Yeah. Just answered all the question. Yeah.
Is that okay? Yeah, okay. Next is from my friend Pak Yunus. Oh yeah, okay.
Thank you, Pak Tirto. Thank you, Pak Yazid. I am Janus, a student in chemical engineering degree in ITB. My question, I have experience about silica when we produce activated carbon from palm kernel. We burn and we take energy by boiler and superheater in the top of combustion room, and we found silica, many silica, and this is coated the tubing and pipe superheater. Superheater is working in the 300 degrees of Celsius under 400 Celsius for activation of carbon. My question is how you mitigation of silica, maybe plug disposition of silica in the surface of your heat recovery. I think this is we think about how to minimize the power of silica. Thank you.
Yeah, it's a very tough question to answer, right? So because the silica itself, the source based on the biomass that we use. Sometimes people use a coating on the tube or to avoid or to mitigate the problem, and some also company provide any chemical additive to the biomass to suppress to increase the what they call melting temperature, so that the silica itself do not solidify on the surface. So there's many things involved inside the problem for the silica deposition. Thank you very much. Yeah.
Is there any other question, Pak Yunus? Okay, thank you. Okay, we will fight again. Yes, we still have until 15, yeah. We still have maybe about 10 minutes. Is there any question? Pak Hendra, okay, first, and then is there any other? Okay, maybe directly to Pak Hendra for the first, I think better, yeah.
Okay, thank you very much, Mr. Mike Suzuki and Professor Yazid Bindar for the insightful presentations. So I have a question for Mr. Mike and Professor Yazid. So for Mr. Mike, I have two questions. So the first question is, how does the Rankine control differ from the traditional or existing control system approach? And the second question is, are there specific industries or domains where the Rankine control has been successfully demonstrated and provide significant advantages? And for Professor Yazid, regarding the crystallinity of the silica derived from the rice husk, so what are actually the factors that can affect the crystallinity of the silica derived from the rice husk? And also, is there any appropriate sectors that can actually utilize both amorphous and also crystalline silica derived from the rice husk? Thank you very much.
Thank you, Pak Dr. Hendra. I think for the first, Mr. Mike, please to answer the questions. Yeah, two questions.
Can you hear me?
Yes, very clear. Okay.
Yeah. Okay. Thank you. And I have got here like two questions. Thank you very much for this question. So the question is so customer already have like existing conventional system. And what is the like additional value for the like Renke control? That's my understanding for this question. And in case of like a legacy system, no, I mean like the existing control system. For example, like let's say you have like a 3 boiler, and normally the 3 boiler control loop is like a pressure-based control. They are trying to keep the pressure level of the like a steam. So the quality of the steam is the pressure, and to control to keep this pressure. So the many existing control loop are doing like pressure, like a PIC control loop, pressure control loop by PID control, and the all boiler is like moving together to keep the head pressure. But our approach is like slightly different. So we analyze for the each individual boiler efficiency energy index, and we are trying to maximize the load of the like a high efficient boiler, and we are trying to reduce the load of the worst efficiency boiler. So depending on the like efficiency, we are trying to allocate the load of the boiler, and then we are trying to like maximize the efficiency of the total boiler efficiency. So that kind of like a load allocation is like the same for the like air compressor or like a chilled water plant. And also the like second question is the like what is the like the target process for the Renke control, and that is a very good question. And since manufacturing process is depending on the industry quite different, or even if it's like the same industry, process is different, so quite difficult. So, but in case of utility plant, for example, like a boiler system, multiple boiler system, or like a cogeneration plant. Cogeneration plant means, for example, like a gas turbine plus waste heat boiler, or like a chilled water system. Chilled water system is a multiple chiller with cooling tower and like a chilled water pump, and also like an air compressor. I use that as an example. So I think those are the one of our target application, and like a compressed air and the chilled water and like a steam and the electricity are used for the like food industry very much. So that those will be our like a target application, especially for the in case of the food and beverage. That's my question. That's my answer. Sorry.
Thank you so much. That okay, Pak Hendra? Yeah. Okay, the next question to Professor Yazid, please answer.
Thank you, Pak Hendra, for the question. Based on our studies and experiment, when we produce the biosilica from the combustion of the rice husk, the main factor is the temperatures. So above the 700, the silica will be formed into the crystalline form. The main reason why we avoid the crystalline one, because it is toxic. For then we aim our product for the pharmaceutical, healthcare, food sensor, drug delivery, and cosmetic. That's why we avoid any fraction of the crystalline to be formed inside. We have no any information yet what the other factor, or probably the heating rate, because the heating rate here is very middle one. So we have not any information about other factor. However, for to use the biosilica to other product, probably if you increase the temperature, and then for like for the electronic use, thermal processing, it might change the phase from amorph to crystalline. So if you have any information, we can discuss that. Thank you very much.
Thank you, Pak Dr. Hendra. Okay, we still have 5 minutes more, to end this session. We will invite again, maybe 1 or 2. We still have questions. If there are any other questions. Pak Janus again. Okay. Mike, is there any mic?
Thank you, Mr. Once again, our question and sharing of our experience. When we burn sodas like rice husk, it's very low density. Then any process to volatilization and gas flow up to furnace. We have how do you mitigate of H2O water produced from burning of biomass. I think contain a C and H, H2O, in end of process for protect dust to release the environment. We have experience with we use back filter like precipitator, active precipitator, and setting disturbed by vapor. I think how do you mitigate this vapor to disturb separation of solid?
Thank you very much, Pak Janus. When we develop the combustor, we start from the cold flow. We make sure that for the fluid dynamic that we set up with the flow of the air itself that we employ, all the rice husks are suspended within the furnace itself. So we find and the right condition operation. And when we move to the design for the hot design for the combustor itself, we make sure the combustion occur right away within the furnace itself. So the flows do not push the rice husk to the top. And for that one, we also install the cyclone. Then why we introduce the suspension furnace is something that can meet the criteria for the burning the rice husk, and also to make sure the temperature is not higher than 700. Okay, thank you.
Okay, I think that's all the questions and also all the answers. Yeah, I think we already got many insights, many new knowledge, about the control systems and about the how to manage waste, especially food waste, from Professor William and also from Professor Rashid. We can add our knowledge about how to combine the production of silicate and production of heat for electricity generation. I think that's all for these sessions. We will end these sessions. I think what committee, how to we will give the certificate virtually or Oh, okay. I will give back the mic to the MCs. Thank you so much. I will go back to the seats. Thank you so much.
Thank you. Thank you for all the speakers and moderator in the plenary session for today's event. Now, we would like to present a certificate to our speakers and moderators. I would like to invite Professor Dr. Insinyur IGBN Markerti Harta to present the certificates.
Okay, so the certificate will be given one by one on screen along session. I think for the first certificate, the operator may show the certificate alongside Mr. Mike on screen.
Yes, I'm here.
Okay,
Let's
give a round of
our
applause
warmest
for
applause
Mr.
to
Mike.
Suzuki.
Okay, for the next one, Professor Yazid Binder, please step forward for the photo session. Thank you, and for the last one, for Professor Tirto, for being the moderator for today's plenary session.
Once again, let's give our warmest applause for our speakers and moderators. For dear speakers and moderators, may come back to their seats. Thank you once again, our honorable speakers and moderators, for joining 2023 Stksr.
Once again, I would like to thank our sponsors and helping us, helping this event to come true. The 2023 Stksr is sponsored by
PT Perkebunan Nusantara as silver sponsor,
PT Ayam Topindo Nuansa Kimia as silver sponsor,
PT Riau Andalan Pulp and Paper of April Group as bronze sponsor,
Pupuk Indonesia Holding Company as bronze sponsor,
Garuda Food and Gokana Ramen and Tepan as sponsor.
Okay, ladies and gentlemen, we have now come to the end of today's plenary session.
After this, there will be a coffee break before resuming to the next session for 15 minutes. We will continue at after 15 minutes. Thank you.